Here we're given a function f of x equals 1/4 x to the 4th minus 2x squared plus 7/4, and we're asked to find part A, the intervals of increase and decrease for the function f, part B, the local min and the local max for f, part C, the intervals of concavity and inflection point IP, and part D, make a sketch. This is a painful thing to do, and I actually spent most of one day just trying to figure out a quick way to do this. So I think I've just about narrowed it down to the easiest way to do this. Now, if you have an easier way, please share it with me because I will adopt it. I would. But here's what I've come up with after thinking about it and redoing problems. First thing I'm going to do, I won't call it step 1, but the first thing I'm going to do is find the critical numbers of f, f prime, and f double prime. So look back at note 84 if you want to review about how to find those. We first take f of x, and we're going to set it equal to 0 and solve for x. Those will give us what's called the zeros of the function. Okay, so the zeros of f are going to be the answer to 1/4 x to the 4th minus 2x squared plus 7/4 equals 0. I can factor the left side, set each of the factors equal to 0, and that will give me 4 zeros or roots of that polynomial. And those roots are positive and negative 1 and positive and negative square root of 7. Now these are just the zeros. There are no values of x for which the function f is none-defined. So that, actually I just found the zeros of f. Those are not the critical numbers. The critical numbers are f prime of x. So let's look at f prime of x, take the derivative of f of x, factor it, set each of the factors equal to 0 and solve. You'll get the zeros of f prime as 0 and plus or minus 2. Those are critical numbers of the original function f. Now f double prime of x is 3x squared minus 4. We calculate that, set it equal to 0, solve. We get x equals plus or minus the square root of 4 over 3, but you simplify it, you get plus or minus 2 over the square root of 3. Okay, so those actually happen to be the critical numbers because there are no values of x for which f prime and f double prime do not exist. So the next step we're going to do is draw a diagram using notes 81, 82, and 85. So you can go and review those notes before you see what we're going to do here, and it'll make more sense. We're only interested in f prime and f double prime in applying these notes. So f prime of x, and by the way, the reason we factored f of x and found the zeros is because later we can use them as the x-intercepts in the graph. So back to this, f prime of x is factored, and f double prime of x doesn't factor. We can just leave it as 3x squared minus 4. And we're going to take a number line, and we're going to do as we did in the last video. We're going to break it up using the zeros or the critical numbers of f and f prime. In other words, the zeros of f prime and f double prime. Negative 2, 0, and 2. All right. First I listed the zeros of f prime, negative 2, 0, and 2. And then the zeros of f double prime. Let's see, what are the zeros? Oh, those are positive and negative 2 times over the square root of 3. Okay, so the lower ones are the zeros of f double prime. The higher ones are the zeros of f prime. So first, let's break up the number line using just the zeros of f prime, or I should say the critical numbers of f. And let's find out what the sign, positive or negative, is for f prime in each of these 1, 2, 3, 4 regions. Do a sign graph. We get negative times negative times negative gives us a negative. Okay, and in the next region we have, well, let's see, does that tell us? That tells us we have a decreasing function. That's because f prime is negative. Okay, the slope of the tangent's negative. In the next region, we get negative times negative gives me a positive. That means I'm going to have an increasing function because the slope of the tangent's positive. The line's leaning to the right. In the next region, for f prime of x, I get positive times negative for a total negative. So I have a decreasing function in that region between 0 and 2. And for the last region, I get positive times positive times positive. So f prime is positive, which means I have a tangent leaning to the right because we have a positive tangent, and an increase in the function f. Okay, this is all about the function f in the long run. Okay, now we're going to look at the regions that are acquired by just the zeros of f double prime. That was negative 2 over square root of 3 and 2 over square root of 3. If we choose a value in the first region, and that would be between negative infinity and negative 2 square root of 3, and evaluate the function f prime, we get a positive. That means we're concave up there. And in the middle region, between negative 2 over square root of 3 and 2 square root of 3, we get a negative value, so it's concave down. And for the last region, we get a positive value for f double prime. That means concave up. All right, now what about local min and max? Well, for x equals negative 2, you see how we're decreasing and increasing? That's a local minimum. And then at x equals 0, we have increasing then decreasing. That makes x equals 0 a local maximum. And then for x equals 2, we have a local minimum because we have decreasing then increasing function. Okay, and then for points of inflection, those are the points, the values of x for which the concavity changes. It occurs at x equals negative 2 over the square root of 3, and again at 2 over the square root of 3. Those are points of inflection. Okay, let's go now to the next video to continue this problem. We haven't even answered part A, B, C, or D. We'll do that in the next video.